All right, welcome. Today, we're going to talk about a choice that might sound super technical, but trust me, it's absolutely critical for so many systems you probably rely on every single day. We're diving into how to choose between a normally open and a normally closed motorized ball valve. Let's dig into why this is such a big deal. So, I want you to start with this one simple question. Picture this. Your system suddenly loses all power. Everything just shuts down. What is the one thing that must happen, or for that matter, must not happen, to keep everything safe? The answer to that simple question is the key to, well, everything we're about to cover. You see, this isn't just about picking some random part off a shelf. Choosing between normally open and normally closed is a fundamental fail-safe decision. It has a direct line to the safety, the stability, and even the energy efficiency of your whole setup. Okay, so let's break down what really separates these two. The core difference? It all boils down to one simple thing. What does the valve do when the power is cut? What's its natural default state? Here it is in a nutshell. A normally open, or NO valve, is, you guessed it, open when it has no power. A normally closed, or NC valve, is closed when there's no power. That default position, what it does during a power outage, that is the fundamental difference between the two. Let's take a closer look at normally open. When the power's out, this valve is just wide open, letting whatever's in the pipe flow freely. If you want to stop that flow, you have to apply electricity to force it shut. The second you cut that power, a spring or some other mechanism just pulls it right back to its default open position. And then we've got the flip side, normally closed. As the name says, with no electricity, this valve is slammed shut, blocking anything from getting through. You need to send it an electrical signal to power it open. But the moment that signal is gone, snap, it automatically shuts right back down. Okay, so now we know what they are. But how do you actually choose the right one? Well, it's not just a guess. Let's walk through a really simple framework that's going to help you make the right call every single time. It all really comes down to asking yourself 4 key questions. And these questions will give you the confidence you need to know you're picking the right valve for your specific job. And here's that checklist. First, and this is the most important one, what is the required safety state during a power failure? Second, think about how often the valve is going to be opening and closing. Third, how does it fit in with your system's overall control logic? And finally, what are the properties of the stuff, the medium, that's actually flowing through it? Theory is one thing, but let's see how this actually works out in the real world. We're going to apply this framework to a couple of super clear real-life scenarios. Okay, first up. Imagine a massive piece of industrial equipment. It's generating a crazy amount of heat, and it relies on a constant flow of cooling water to stop it from overheating and basically destroying itself. So let's go back to our big question. If the power goes out in this factory, what is the absolute safest thing that can happen? Do you want that cooling water to stop, or do you need it to keep flowing no matter what? The answer here is pretty obvious, right? That water has to keep flowing. So for this application, you absolutely need a normally open valve. In its default no-power state, it stays open. This makes sure that the cooling circuit keeps running and protecting that expensive equipment even when the lights are out. Now for a totally different scenario, one that's probably a little closer to home for all of us. The main gas line that comes into your house. Let's ask that same exact question again. If there's a power outage at your house, what's the safest possible state for that gas line? Do you want gas to keep flowing into your home, or do you want it to shut off immediately? Yeah, this one is a total no-brainer. You need that gas to stop, and you need it to stop instantly. This is a perfect example of why normally closed valves are so critical. Its fail-safe position is closed, which means it cuts off the gas supply and prevents a potentially catastrophic leak the very second the power fails. So let's bring all this together. I'm going to give you a quick little cheat sheet to summarize these decision points. This should help you make the right call every time. This right here, this lays it all out for you. It all starts with safety, right? Does the flow need to continue or does it need to stop? But it goes deeper than that. Think about energy efficiency. If a valve is going to be open 99% of the time, choosing a normally open one saves a ton of power. And of course, the opposite is true. Your control logic plays a huge part too. And finally, the medium itself matters. If you're working with something that could solidify or clog things up, a normally open valve might be the only safe bet to prevent a blockage. Ultimately, it all comes back to this one idea. This choice, it's not just some minor technical detail. It's fundamentally about making sure your system works safely and efficiently. especially when things go wrong.
So I'll just leave you with this thought. The next time you're designing a system or you're just picking out a valve, forget all the technical jargon for a second and just ask yourself this one simple question. When the power cuts out, is the safest state for my system on or is it off? Your answer to that will tell you everything you need to know.